Okay, I'll just stop you there. If you haven't quite finished those questions, you can come back to them later. But I think most people have finished. So I want you I'm going to skip the Van de Graaff generator for the moment because it's not set up, and I'll get that going ready for after lunch. So we're going to move to page 12 and look at a little bit more in depth about these terms, isotopes and relative atomic mass. So we just, like literally seconds ago, we talked about isotopes. Is there someone who thinks they can explain to me what an isotope is? Mr.
So an atom has the same number of protons with different number of neutrons.
Okay. Yep. Is everyone happy with that? Good. Anyone want to have a stab at relative atomic mass?
Is that like the average atomic mass for an element?
It is. It is like that, yes. And so where these two terms come together is we know that isotopes, so we were talking about carbon-14, carbon-13 and carbon-12, and we were saying, well, they're all carbon.
Oh, that's right. I think I know how to explain it.
Okay, so you're going to have a go?
So, if you've the different types of the particular type of atom, their abundance, like the percentage, if you multiply that percentage by the type of the atom, they are like 14, 13 or 12, and then you add them all together, that'll give you the relative atomic mass.
Yes. Yep, that's the mechanics of it for sure. Yeah, so we're looking at the percent abundance in nature. Yes, so we have to start with that. We need to know the percent abundance. And then we weight it accordingly. So the more abundant one is then going to contribute more to the overall mass. So that's true. But it's relative to what? Because whenever we measure the mass of something...
Isn't it relative to the protons?
No. We need to be able to measure it against something. So for a very long time, there's been a piece of platinum in France that's the kilogram. And if they hold it in a sealed, environmentally controlled bubble, very precious lump of platinum. It's platinum because it's quite unreactive. But people come around from all around the world to measure their lump of whatever against this lump of platinum, which is by definition the kilogram. And then you take your one back to your country and everything's measured against it. So that we all know what a kilogram is. Because otherwise, what's a kilogram? A kilogram is something we've made up. A litre is something we've made up. Okay? A metre is something that we've made up. So what is it, and how can we make sure that if I measure a metre, it's the same as you measure a metre, or someone, in Turkey measures a metre? How do we know it? It's all the same. And in fact, this has caused NASA some trouble, especially landing on Mars. Well, not landing on Mars, as the case may be, crashing on Mars, because they got their units mixed up, and they had outsourced some of their equipment to some countries who were using imperial measurements, like feet and inches, and then other countries that were using metric measurements, and so when they came together, it was wrong, and they fire this probe off to Mars, and it crashes. And so it has to be relative to something. So our kilogram is all relative to this lump in France, lump of platinum. When we talk about our masses of our isotopes, what's it relative to? I shall tell you.
Thanks.
It is relative to 1/12 of the mass of a carbon-12 atom. And this actually has changed over the years. It's been oxygen, it's been hydrogen in the past, but now we've settled on carbon. Carbon-12, it's abundant. This is a stable isotope. It's readily available. It's easy to measure. And so we're measuring all of our masses and saying that the unit of 1 is equivalent then to 1 subatomic particle from a carbon-12 nucleus. Does that make sense? Okay. So how are we going to measure such tiny masses? We're going to measure it using a mass spectrometer. And I've started to draw up a mass spectrometer. And you can see there's an analogy on page 12. The idea here is that if you were rolling balls down a ramp, and they're metal balls, so large metal balls and small metal ball bearings. And at the end of the ramp, it goes past a magnet. You can see in the picture that the ball bearing with the smaller mass is going to be deflected more by the magnet than the ball with the bigger mass. Okay, because momentum is going to keep that bigger one rolling further. Lighter and heavier aren't really helpful terms necessarily, but it should make sense to you that the smaller, lighter one there is going to be easier to deflect, easier to change the direction that it's travelling in when it goes past that magnetic field. Well, it's exactly the same for our real mass spectrometer. Now, what we need to do is vaporize our sample. What does vaporize mean? If we turn something into a vapor, what do we do to it?
Make it gas.
Yeah, so we're going to turn it into a gas. And then we are going to accelerate it so that it's going nice and fast. And then we've got some magnets. So we're using the same, it's the same sort of process where we've got our charged particle, and it's going quite fast, and now we're going to move it past a magnet and deflect its path. And so one with the smaller mass is going to end up over on this side, isn't it? And the ones with larger mass are going to end up further along. Okay, so if we had our sample, and just say it was magnesium metal, like that. We've vaporized it, we've made it into a gas, we've accelerated our particles past the magnet, and then we're going to detect along here, detect and see, well, how many of each. They can only land in whole numbers, okay, because they can only have whole numbers of protons and neutrons, which is their masses. And the frequency with which they hit at that particular point is going to tell us the relative abundance. Okay, so this is 24, 25, 26, and you know, this one's going to get hit a lot. So we end up with quite a tall peak there at 24. we have a smaller piece at 25 and 26. So in this way, we can see which isotopes are present for that element, and also the relative abundance based on the percentage of strikes we have in each of these positions. Does that make sense? Or has anyone got any question about that? And then we can go on to then calculate the relative atomic mass by looking at those different the peaks here. So if this one was 79%, this one was 10%, and this one's 11%, then as Jack was saying before, we can work out the relative atomic mass of magnesium by finding how much mass is contributed by each isotope. Okay, by just converting that percent to a decimal, multiply them all together, we get 24.32. But because, in actual fact, we were given these percents to 2 sig figs, we really should round this to 24. You do need to know how a mass spectrometer works. That's on the course. And the second example on page 14 is for chlorine, which has the 2 isotopes, chlorine 35 and chlorine 37. And we're told that, so if we have chlorine, we have chlorine 37 and chlorine 35. 37, it's about 24%, and chlorine 35 is about 76%, according to how they're found in nature by doing this to it. And it's the same calculation then of 0.24 times 37 plus 0.76 times 35 gives me 35 point, we'll end up with 35.5. And that is its mass relative to 1/12 of the mass of the carbon-12 atom. So yeah, any questions or any comments or anything?